All right, ladies and gentlemen, if you look up here at this picture, a couple things you may notice is, what colors do you see?
Gray, white, red.
Gray, white, and red. Now, in general, white usually represents a hydrogen, gray represents a carbon or black, and the red represents an oxygen. Now, one thing you might notice in this picture very quickly is the red one up here. How many things is it attached to? Two. Now, this red one up here is only attached to how many things? One. So there's something a little bit different about the reds. But the white ones, how many things do the white ones attach to? One thing only. The gray ones, though, have some unique characteristics. They tend to attach to 4 things. Sometimes they have 2 lines, and sometimes they have 1. We're going to learn a little bit about organic chemistry and nomenclature and how molecules like this behave in chemical reactions, and also how we can predict their reactions. So this is Introduction to Organic Chemistry and Nomenclature. Yeah, sometimes happens to the best of us. As erosion happens, as changes happen in organic material, we're going to look at those changes right now. Some of them are decomposition reactions. Other ones are organic reactions as organic materials are changed. Organic chemistry is the study of carbon-containing compounds and their properties. So when we talk about organic chemistry, it's carbon-containing compounds and their properties. The vast majority of organic compounds contain chains of rings of carbon atoms. So many organic chemical compounds contain rings of carbon. Organic molecules are the chemicals of life. They are found in and produced by living organisms. That's why they're called organic in general. Common elements in organic compounds: hydrogen, boron, carbon, nitrogen, oxygen, fluorine, silicon, phosphorus, sulfur, chlorine, bromine, and iodine are also commonly found in organic compounds. Carbon atoms form the basis of organic molecules. Your methane, ammonia, and water. Because a carbon atom can form up to 4 single covalent bonds, that's why it forms such chains. It is the molecule, it is the atom of life, the backbone of life, as it's commonly referred to. It can also form multiple covalent bonds. This is a single bond where 1 pair of electrons is being shared, represented by a line. A double bond has a double line, where 2 electron pairs are being shared. That's a double bond. And it can also have a triple bond, 3 electron pairs being shared. Cannot have a quadruple bond, even though some people would say it would make sense. It does not have a quadruple bond. This leads to molecular variation in complexity. This is the basic carbon framework of a steroid. This here, does anyone know what that molecular structure is? Okay. That happens to be DNA, showing all of the atoms and their bonding connection. You will notice, though, in between the DNA, you can even see there is a gap in the middle. Gap in the middle, that space in between the DNA is why the DNA can zip and unzip, and it is connected together by what are called hydrogen bonds. So we have all these organic molecules here. This molecule, this DNA double strand, can connect together, but it's all based on a single hydrogen connection, a attraction between the 2 strands. Now, hydrocarbons are elements that are composed of hydrogen and what? Carbon, of course. There are 2 main classes. There is the aliphatic and the aromatic. Okay? The aliphatic group is composed of alkanes, alkenes, and alkynes, and then the cycloalkanes. The formula types. If you have something like this, yes? It is not something we will look at alkanes, alkenes, and alkynes in specific. Aromatic compounds are the ring ones. Okay? So the classification is important to know. There are different types, and that's about it for hydrocarbons. Not the most important for naming them. The formula types, though, usually give you more information about the names. Okay, this here is a structure. Okay? The structure is usually a drawing representing the bonds and the connection between the atoms in a particular formula. This is called a structural formula, even though it's a picture. Structural formula. This here is called a molecular formula for the same structure, that same molecule, C3H8. And this here, when it is extended out here, is a way of showing the structure in the formula. Okay? So structural formulas are often drawn like this, but when you reduce it down, you can draw it like this, where you have the CH3, CH2, CH3, representing the CH3 here, CH2, and the CH3 there for this particular molecule. So usually the best thing to have is the structure drawn out, but the structural formula can help if you just have that and not have the whole entire structure. The prefixes represent the number of carbons in a hydrocarbon chain. So if you have one carbon, the prefix for one is, take a guess? Yeah, you would think it'd be mono. Yeah, you'd think it'd be mono if you're dealing with prefixes in covalent nomenclature. Unfortunately, with hydrocarbon chains, the prefix for one carbon is meth. Oh, yeah, meth, of course. Meth is number one, sure, yeah. Duh, of course I knew that. No, I didn't expect you to know that. Everybody guessed the same thing. The prefix is 1 for meth, 2 for, this is the best one, F. Yeah, it doesn't even sound like anything you would think of. Die, by, no. No. The three is a cool one. It's called pro, which is the prefix for something like propane, ethane, methane. It's a number of carbons. Okay? The next one is the favorite one of most regular chemistry students. And it is called but for regular chemistry students until they learn that it's actually but, not but. So, yeah, butane. No. Butane. All right, so we'll have fun with that, not too much fun. 5 is pent, 6 is hex, 7 is hept, 8 is oct, 9 is non, and 10 is dec, which all makes sense. So all of these make sense. All of those kind of different. So if you can remember 1 through 5, you're set for the rest. Because they are the same prefixes as most things. So this list is important to know. The next thing is the prefix is represented by those number of carbons. The suffix is represented by the type of chain. This here has all single bonds. All single bonds, no double bonds. Okay? The carbon-carbon bonds are all single. That means it's saturated. So a saturated hydrocarbon is one that has only single bonds. Only single bonds. If it has only single, the ending is ane. Alkane is the class. It is called an ane ending. In this case, we have 3 of these, so that's prop, ane, that's it. Okay. So if we had 2 carbons, it'd be ethane. If we had 1 carbon, it'd be methane. If we had 4 carbons, it'd be butane. Thank you. Or butane for those that are still in regular. Or just like saying it. That's fine. I know. Got to make some chemistry fun at times. The names are definitely fun. All right. Unsaturated contains carbon, multiple bonds, like double or triple bonds. It's called unsaturated. It's not the same either way, though. So double bonds The formula CnH2n. This is classified as an alkene. So ene is double bond. And then if you have a triple bond, it's called an alkyne. And this is the general formula for an alkyne. You're going to have less hydrogens because you got a triple bond there.
Is that, then would it be propene and propane?
Yep, very good. This one is, this one happens to be propene, and the location of the double bond happens to be on the first carbon. So you count them up, you got 1, 2, 3, or 1, 2, 3. So the ENE is at the first carbon going this way, or the second carbon going that way. So you look at what's less, 1 or 2.
1.
1 is less, so you count from this side. So this could also be called 1-propene, because that's where the double bond is located. Although in this case it doesn't really matter, because if you flip it to the other side, you have no options. But if there's a longer chain, that's how you would identify where the double bond is located. Yes?
Could they have multiple double bonds?
Absolutely. So if they have multiple double bonds, I think I get to it next. We'll look at that. If I don't get to that, I'll tell you how to do that. So nomenclature rules.
If you have a triple bond and double bond in the same one, would you have a second bond?
You would include both in the name. So these are the rules for how to do that. Yeah. So now we're going to get into the rules for how to name them. We got prefix and suffix. How many carbons are in this molecule here?
7.
7. So what's a prefix?
That's
Hept. And what is the suffix going to be with all single bonds? Heptane. Very good. So use the prefix for the number of carbons in the longest continuous chain of carbons in the molecule. In this case, longest continuous chain is 7. There's no other smaller chains. That's the first rule. 1, 2, 3, okay. Hept. There we go. Then you have the suffix for the longest continuous change. In this case, it's an ane because they're all single bonded. So that's basic nomenclature for a hydrocarbon. Alkyl groups. This is an alkane less than 1 hydrogen atom. So you replace the ane with a YL. So if you have 1 less hydrogen atom, you'll have an alkyl group. It will change. Can you put your bag on the ground so we don't break any of the things that are drying right there? It'll help prevent you from hurting yourself or getting dirty Kool-Aid on your bag. Okay. Yeah.
The last slide. What if there were like more than 10? How would you?
It keeps going past that. There's what is that? There's 11. Nonane, decane.
11.
No. Yeah, 11. I can't remember the prefix for 11. What? Do I say poly? No. There are actual prefixes for them. Depends on how long the organic molecule is. But yeah.
How would you lose a hydrogen and still have a single bond everywhere?
So lost a hydrogen is have a single bond everywhere. Yeah.
Well, the next slide, that's what it says.
That's what it says. It doesn't seem possible to me either. No. Let's look at an example here. So, if you had CH3 here, what is meant by an alkyl group is this here can attach to something else. It's not stable by itself, so this could attach to something else, and it's called an alkyl group. So this would be a methyl group, methyl group.
So the other bond would bond with the base.
Yeah, it wouldn't be a molecule. It would have to be a part of a larger molecule. So this is a methyl group. Okay, a group is not an entire molecule. So this is an entire molecule, methane. This is a group that attaches to something else. Yeah, I totally follow what you were saying. Is absolutely true. It couldn't be by itself. Wouldn't work. But if you have CH3 here, this is called ethane. Okay? If you took off one of the hydrogens, CH3, CH2, this is called a what group? Okay, an ethyl group. So you can have a methyl group, an ethyl group, a propyl group, a butyl group, so on and so forth. You can have all these groups attached to the longer chain. So you got the long chain, and then when it's attached to the smaller pieces are called these groups here. So here's how it works. You've got the methyl, the ethyl. Here this would be an N-propyl, depending on where it's attached, an N-butyl, an isopropyl. Slightly different shape here. It is attached here to a larger hydrocarbon, and the carbon in the middle and 2 carbons on the side. So N-butyl, N-propyl means it's just in the chain. T-butyl means it makes a T. Literally, if you put it on its side, that's a T. And it stands for tertiary, which means it's got additional things on it besides additional groups. So this is a T-butyl. It's got 4 carbons. Some people even look at it and say, oh, it looks like there's 3 different methyl groups attached, but it's this whole group that's attached to the larger carbon chain. Nomenclature rules. When hydrogen atoms are replaced by other groups, the names must indicate the location of carbon atoms where replacements are made. So in this case, boom, we've got this carbon-carbon chain, 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. Either way we go. You want a number in the direction that gives the smaller numbers for the location of the group. So you want the numbers to be the smaller if you have an option. So you number from this side, 1, 2, 3, 4, 5. The methyl group is on the second carbon in this case. If you look at it in this way here, we do 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We would have to number from left to right. We can't number this way because the group is located off of that carbon there. So this would be carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. And some of you are also seeing, wait a minute, could this be carbon 1? Yep. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. And this could be the methyl group. It's the same thing. So renumbering those. Winner, winner, chicken dinner. There you go. All right. I like chicken dinners too. Although I like steak sometimes. And tofu is really good. Okay, sorry. Sorry, I got distracted. I got hungry. Yeah. This one was CH. If this was something else like CH2Cl or something, then you start counting here because that's the hydrocarbon chain. And then this would be some group that has it wouldn't because it wouldn't be stable. CH2 would have to have a double bond. All right. So where the group is positioned, the methyl branch is located on carbon number 2. Once you know it's on carbon number 2, you write the location. So in this case, you've got your 2-methyl. You write your location. 2-methyl, which means it's on the second carbon. Then you follow by the name of the parent chain. So this parent chain has how many long? How many carbons? 5 carbons. So what prefix? Pent. And are there any double bonds? Nope. All single bonds. So it should be pentane. 2-methylpentane. 2-methylpentane. These two molecules are exactly the what? Exactly the same. They're just whoop, flipped around. 3 dimensions. So let's look at this one here. When there's more than one alkyl branch of the same kind, you wrote the location, number, and then you use a prefix. So in this case, if we number from the left to right, we've got 2. We have one of them at 2. We have one of them at 3. There are 2 methyl groups, so you use di, saying that there are 2 of them. You already said there were two of them, one here and one here, but it's just to re-emphasize that there are two of them, and then two methyls in the hexane chain. So that's how we can name that one. This one here is a little bit different, right? On this one here, you have a methyl at 3. But you have another methyl at what? 3. So you have how many methyls? 2. So you have 3,3-dimethyl hexane. So this is why you show the number and you show the amount. Kind of a duplicate, but it's to prevent any errors, and that's the nomenclature rule for those. So here's the methyl group. Here's the methyl group. They're attached to that carbon, central carbon there. What? CH3 is a methyl. Yep. All right, let's look at this one here. I'd like you to try to write the name for this molecule here and this molecule here. Actually, top one first. Do the top one first, and then we'll go to the bottom. Oh, there it is. So when there are different alkyl branches, you write the location number, then the group, or the number prefix group in alphabetical order, irrespective of any prefix. So in alphabetical order, irrespective of any prefix. So on this one here, we know the position. We've got a ethyl, because ethyl comes before methyl in the alphabet. So you write the ethyl first. 3 ethyl. Then you write the 2 methyl.
Wait, what?
And it's hexane. It's got CH2, CH3. It's got 2 carbons in it. And no double bonds. Yeah.
What else am I making?
The number of hydrogens are going to be the same.
Always be 5 hydrogens. Based on the formula. All right, let's look at this one. This one gets a little bit crazy. We know the numbering system starts from the right. First of all, got to start from the right because we got a group here. And this one, it would have been 1, 2, 3. This one is 2. So 2 is less than 3. We number from that side where the group is. Then we know we've got a 2-methyl somewhere in there. Right? But we've also got something at the 4th carbon. We've got a 4-methyl. And we got a 4 what? And a 4-ethyl. So the ethyl wins because it's got the alphabet behind it. 4-ethyl. And then you put the 2,4-dimethyl. And there's a methyl here and a methyl there. 2,4-dimethyl. And then the last one you put in there, of course, is your hexane. And it's all written as one word. So that's the nomenclature rules when you have different groups, the methyl, ethyl, and so on. Now, the cool thing about alkenes and alkynes is they have the same rules as the alkanes. Same rules as the alkanes. When the chain has 4 or more carbons, number the chain to give the lowest location number to the double or triple bond. So you want to number it from the side that's closest to the double or to the closest to the triple bond, respectively. So in this case here, we've got 1, 2, 3, 4, 5 carbons. Which side should we number from, left or right? Left side, because the double bond is off of the 2 carbon. So this would be called 2, Got 5 and ene ending, 2 pentene. This one here, how many carbons do we have? 4. What's the prefix for that? Yeah, very good. And the ending, the YNE. And where's the triple bond located? Okay, carbon 1. So that is our 1-butene. There we go. That's it. Same rules there. Now, when the chain has multiple double or triple bonds, you designate them by number prefix. So you've got this one here. 5 carbons long, so it's going to be pent. It's got double bonds, so what's it going to end as? Pentene. And where are the double bonds located? 1 and 2. And use the prefix for 2 things. 1, 2, dipentene. All right, there you go. 1, 2, dipentene. Okay. So another way of writing this here is 1, 2, pentadiene. Okay. So these are both acceptable ways of naming it. Okay, this one here tends to fit in with what we are commonly using, at least our pattern. Some people like this because it says that you have 5 carbons and you have 2 double bonds. The ene says it's a double bond. So that's why some people like this technique here for naming. Yeah? Alkanes? We don't have any. We don't have any alkyls yet. It's all part of the longest chain. Since it's part of the longest chain, it does not. We do not designate it. But I'm sure if we add some alkyls on, we'll have to name those. So let's take the name 2-hexyne. Please draw the structure and structural formula for 2-hexyne. Alright, so how do we get from name to structure? Let's look at how you can do this. Again, usually the first thing you can do is you write the carbons in the root chain single file. So how many carbons do we need in this one? 6. So I'm going to put all 6 of them. 1, 2, 3, 4, 5, 6. Okay, so they're spread out. Then connect the C's with single bonds. They all have to be connected together in some way. So we just put lines in between all of them. Okay, that's our basic hex structure. Next step is to add extra bonds, branches, and functional groups on appropriate carbons. So what do we have going on our second carbon? Triple bond. So if we count from this side, it's going to be that carbon. If we wanted to, we could count from that side as well, but that's just, most people don't like that. But that's okay. So add our triple bond there. Then the last step is you add hydrogens. Keep adding hydrogens until every C has a total of 4 bonds. Yes? Nope. Nope, it would just be whoop, around. It's exactly the same. There's no difference. So, in this case here, this carbon's only got 1 bond, so I'm going to want to add 3 hydrogens to it. The next one, how many bonds does this carbon have? Already got 4. 1, 2, 3, 4. This one has 4, so they're happy. This one here has got 2, so it would need 2 more. And so on and so forth. And then you write it in order. CH3, this is the structural formula. CH2 is there, CH2 is there, CH3 is at the end. Again, that's the structural formula, not the molecular formula.
Why couldn't it be C2 for the triple bond?
This here?
Yeah.
It's showing that the C's here, it's showing that they each are connected, and usually this particular way of writing it, it's also called an extended formula, shows the C's as separate instead of together. If you had a C2 there, I guess it wouldn't be the worst thing in the world, but you're trying to figure out, okay, there must be, when you see this here as well, CCC, there's 3 C's in a row, there must be a triple bond in there.
Yeah.
When you see the different combinations, you can identify triple and double bonds. So that's why some people like this. I personally like that, if you can do it. All right, name of the following compound. Name of the following compound. First of all, what's the longest chain? All right, let's check this out here. Okay, we know there's 8 carbons. Okay, why do we start on the right side? There's a double bond there. That takes precedent over any groups, okay, in the numbering. So in alphabetical order, we've got 5 ethyl, 7 methyl, 2 octene, representing the double bond in the octene. Ethyl here, it's got 2 carbons here. C2H5 is the ethyl group. CH3 is the methyl group. The ethyl group's off the 5th carbon, the methyl's off the 7th carbon. And it's alphabetical order, that's why the ethyl's written first. All right, let's try another one. Let's go from name to structure. Name to structure. So this is how, oh, I'm sorry, I put it at the 3rd one, didn't I? Yeah, sorry, I put my methyl at the 3rd carbon, that was wrong. I was counting wrong, which was really silly. All right. So this here should be the structure of 2-propyl-4-methyl-hexane. You can also draw it from the other end, it's the same molecule. Yeah, just some fun signs for what is the best thing to do. What is the name of the following compound here? All right, if we look at this compound here, okay, this compound here, a lot of people would say it's 3-methyl-4-propylhexane. We could have something else. Yeah, you should have something else. Gotta look for the longest chain. 1, 2, 3, 4, 5, 6, 7. There's the longest chain right there. Like that. There's the longest chain. So, don't worry about the little things. Look for the long bridge. 4-ethyl, 3-methyl, heptane, because it's got 7 carbons in its longest chain. 4-ethyl, 3-methyl, heptane. Okay, now this one here is another way of drawing the same thing. Okay, whoop, it's got 7 carbons all the way across. So this is one way of drawing it. This is just another way of drawing it, where it's going like that. They are the same exact thing. Okay, same exact thing, even though they're drawn differently. Now, if you have a structure, the structural formula would look like that for that molecule. Parentheses, you'll notice, are for the groups. So, parentheses, this is a methyl group, this is an ethyl group. So the parentheses indicate the groups when they are attached off of the main chain. A condensed formula, which includes all the amount of atoms, C10H22 would be the condensed formula for this particular molecule. So what's the benefit of having a structural formula? Okay? You can have an idea of the structure more. Okay? You don't have to draw it out quite as much either. Condensed formula just gives you the total number, which may or may not be beneficial depending on if you're looking at the structure. Now, when you look at structures, structures are key for understanding some organic chemistry. These two molecules here have the same number of carbons and the same number of hydrogens, but they have different structures. These are called structural isomers because they have different structures even though they have the same molecular formula. This one here is known as 2-methylpentane. This one here is known as 3-methylpentane. Same number of carbons, same number of hydrogens, but the methyl group is located at a different place. If we look at this one here, is this an isomer? What would be the name of this molecule here? That one here also is 2-methylpentane. It is not an isomer. It is just the methylpentane, whoop, flipped around. You flip it around in 3 dimensions. This end and this end switch. That's why that CH3 would be located there. Not an isomer. So if you look at this, methane, ethane, and propane do not have isomers. But butane can. Got more than 4 carbons. Isobutane is an isomer of butane. That's funny. Why is it called iso? Maybe it's an isomer. The first one that has an isomer. Carbon chain. If you have a small carbon chain, no isomer is possible. Yeah?
But for the past slide, so when you flip it around, you just count the one with the branch thingy. But then if there's like the double bonds or triple bonds, you count that.
Yeah, count from that side first.
Okay.
Yeah, exactly. So if there was a double bond here, it would totally change it. We'd count from this side, and then this would be on the 1, 2, 3, the 4th carbon. We have to have double bond in order for that counting rule to apply. All right. So, a question about structural isomers would be something like this. How many structural isomers does pentene have? Oh, sorry, pentane, pardon me. So to determine the number of structural isomers, what would we have to do? Okay. Start drawing structures and seeing if we can draw different structures in 3 dimensions. Okay. So to do this, we know we have the first isomer that is the simplest one with 5 carbons in a chain. Okay? Here we have 5 carbons, but 4 of them are in a chain. With this here, it's no longer named pentane. That's correct. The name is going to be different. You're looking at C5H12, the number of isomers it has. So this is called 2-methylbutane. If the name was the same, then it would be exactly the same molecule. It won't be an isomer. So when you're asking about isomers for something, you're looking at the formula and trying to rewrite it in a different way. This is another way you could do it. You could have the 2 methyl groups on the carbon propyl chain, 2-dimethylpropane. This is 2-methylbutane here with the second, the methyl group. Now, these molecules all look different and they function different. They have different shapes and sizes, so they have different chemical properties. So all of these, because of their structure, they have different properties, and that's why isomers are so important to chemists. Cycloalkanes are alkanes that are connected together. This first one is cyclopropane with 3 carbons in a ring. Cyclobutane, cyclopentane, and then this is called cyclohexane. They all have single bonds, and that's why they're called cycloalkanes, because they only have single bonds between the carbon and hydrogen. They have the general formula CnH2n, where n equals 3, 4, 5, 6, 7. You can't have, obviously, a ring with less than 2, with less than 3. Cycloalkanes, there are 2 main forms that they're found in. This here is called the chair form, where you have your hydrogen sticking up the axial position, and then a hydrogen at the equatorial position. And then if it looks like this here, it is a boat form for the cycloalkane. When you have more than single bonds, this is when you get what are called the aromatic hydrocarbons. Aromatics have their own classification, because you'll notice here that it has a single bond, a double bond, a single bond, a double bond, a single bond, a double bond. This representation is meant to show that the electrons are being shared in this ring. This is called a benzene ring, or a benzene structure, and the way the electrons are actually shared make it a completely flat molecule, completely flat in its shape. It's also drawn like this here to represent the 6 carbons, and the electrons are shared throughout the whole ring. So the electrons are not confined to a particular location, they're shared throughout the whole thing. Some people would even say that these bonds are 1 1/2, 1 1/2, 1 1/2, 1 1/2, 1 1/2 instead of 1, 2, 1, 2, 1, 2. Because you can't figure out which one. There's no difference between the bonding. So it's a completely shared ring structure. To name aromatic compounds, then you've got the benzene, you've got an ethyl group attached, so it's called ethylbenzene. Here you got a chlorine, so it's called chlorobenzene. Here you got an amine, so it's called aminobenzene. Here you got a nitro, NO2, so it's called nitrobenzene. And then here, if you have more than one thing on it, you number from the top and go around like a clock. So this is at 1 and 2, 1, 2 dibromobenzene, and then 1 and 3 dibromobenzene. So that's how to name benzene. So organic compounds, a lot of fun because you have a lot of structures and you have a lot of little bit of naming that goes with it. Okay, things we know about. On Monday we have our ion quiz.